Alright, so in this video we want to discuss the net positive suction head, which we also sometimes abbreviate as NPSH. And what is the net positive suction head? Well, it's a key concept in pump engineering, as it tells you whether pressure at the pump is high enough to avoid cavitation. So cavitation is just the formation of vapor bubbles that could potentially damage your pump. So we define two types of NPSH. We have the NPSH-A, where A stands for available, and that NPSH-A is nothing but the absolute pressure at the suction of your pump, so basically before it enters your pump, minus the vapor pressure of the liquid. So you see here, this is the concept of vapor pressure of the liquid, which tells us that this is a property of the system. And then we have the NPSH-R, where R here stands for required. And that's the minimum pressure required at the suction for your pump to operate normally. So that minimum pressure required at the suction must be exceeded. For the pump to operate correctly. And the NPSH is given in meters or in feet. So it's expressed in meters or in feet. So we're going to keep the SI units, so we're just going to express it here in meters. So now let's see how we can determine the NPSH-A, which is a property of the system. For that, we're going to come back to our Bernoulli equation, which we will write between, let's say, a tank. So let me try to represent a tank, which is connected via a pipe to a pump. All right, so here we have a tank filled with some liquid. Here we have a pump, and we are going to write our Bernoulli equation between station 1, which is on the surface of the liquid in that tank, and station 2, which is at the suction, so right before the liquid or the fluid, which is the pump. So if we want to write that Bernoulli equation between station 1 and station 2, we are going to consider, so potentially initially you have kinetic energy term, so we write it V1 square. So that's the average velocity station 1 divided by 2. I'll drop the kinetic energy correction factor. Remember, there's an alpha here, but I'll consider that this is 1 in the first approximation. We have also the potential energy term, which is GZ1, and we have the pressure work, P1 divided by the fluid density, and that equals to basically the average velocity 2 square divided by 2 plus GZ2 plus P2 over rho, and we may potentially have some skin friction losses, which we'll write here, some of the forces. We remember it represents friction losses. Okay, so now let's see how from this equation we can find our NPSHA. So remember, NPSHA or NPSHR also, they're both expressed in meters. So it could simply correspond to an elevation, Z1, Z2, they're all expressed in meters. All right, so first, let's see how we can simplify that equation and correlate everything to that NPSHA. First thing I want to do is I want to draw that term, skin friction loss. We're going to consider that they're negligible simply because the pump is quite close to the tank. Okay, so there's minimum friction losses due, to the transport in the pipe itself. Of course, if there's multiple turns, changes in direction, then we may not be able to neglect this term. But we're considering here that there is very few turns, which will be reasonable, that the pump again is close to the tank. Then we're looking at the limit pressure, right? That the pressure that must be exceeded, and that is depending on the fluid that we're transporting, the liquid, right? So the minimum pressure at station 2 corresponds to the vapor pressure of the liquid. Okay, so we're going to have P2 equals to vapor pressure of the fluid, liquid. Okay, so now the head which is associated to that vapor pressure if we have P2 equals to PVP, then we're going to have Z2 corresponds to NPSHA. All right, so that's our head. That's the basic NIM head for our pump to operate correctly here. Then what else can we do with this equation? Right, we have two kinetic energy term here. We have V1 square and V2 square. And what we're going to do is consider that V1 is much less than V2. And we're going to we're going to consider that this is reasonable by writing our mass balance equation in steady state, which tells us that the mass flow rate at station 1 equals to the mass flow rate at station 2. Mass flow rate, I call that m dot, and this is expressed in kilogram per second. So m dot 1 equals to m dot 2 means that, let me continue on the next page. M dot 1 equals to rho 1 V bar 1 A1, where rho 1 will be fluid density at station 1, and A1 is our cross-sectional surface area. And here is cross-sectional surface area of the tank. That's very important. M dot 2 equals to rho 2 V bar 2 A2, where we have similar concept, right? Rho 2 is the fluid density, so that's going to be at station 2, and that's also in kilogram per cubic meter. And A2 is the cross-sectional surface area of the pipe, and this one also is expressed in square meter. So key words here are probably tank and pipe, since of course the tank is much wider than the pipe, so we're going to have A2 which is much less than A1. Besides, we have the fluid doesn't change, right? I mean, the fluid density doesn't change. It's an incompressible fluid. So we have rho 1 equals to rho 2, and we can drop the subscripts and just write as rho. And so with all this consideration, we can consider that V bar 1 is much, much less than V bar 2, right? Because you would have m dot 1 equals to m dot 2, so V1 equals to V2 times A2 divided by A1, and because A1 is much greater than A2, then V1 is going to be much less than V2. That's the idea here. So if we get back to our previous page, we've proven that the average velocity station 1 is much less than the average velocity station 2. So now we're going to take that equation, or Bernoulli equation, and we're going to rewrite it considering everything we've just said. So let's get back here. So that term V1 squared divided by 2, we drop it. The friction loss, we drop them. Z1, keep it. We still have P1 over rho. We keep the average velocity at station 2. Z2 is our NPSHA, and P2 is our vapor pressure. So we get GZ1 plus P1 over rho plus, equals to the average velocity squared divided by 2 plus G N P S H A plus P VP divided by rho. Okay, now we want to solve for the NPSHA because it's what we want to try to find, or this is actually the quantity that we want to discuss. So we're going to have GNPSHA equals to, so we still have P1 here over rho minus PVP, the whole thing divided by the fluid density. And we have plus GZ1. So Z1 corresponding to the elevation of the tank compared to that actually of the pump, which would be Z2 or NPSHA. And let's not forget O minus V bar 2 squared divided by 2. And I've already dropped the friction losses. So that's pretty much what we have here. Okay, and if we just want to have our NPSHA highlighted, then that will be P1 minus PVP over here rho G plus Z1 and minus V2 squared divided by 2G. Okay, so that's what we want to discuss now. The goal is to have a pump that operates as correctly as possible to avoid cavitation. So in general, we will want that the NPSHA that we find from basically this equation, which is again a property of the system because we have our PVP right here. So we want our NPSHA to be greater than NPSHR. Okay, so given by the supplier, by the pump supplier, and here you can determine it basically determined from the Bernoulli equation and for a given system. So your supplier would tell you, okay, the NPSHR is, I don't know, 2 meters. And you want to make sure that your NPSHA is going to be greater than your NPSHR. If not, then there's something you can do. Like by just looking at that Bernoulli equation, you can actually try to increase the NPSHA without changing the fluid, right? Without changing the liquid that you're transporting. And what can you play around with? You want your NPSHA to increase. So how to increase the NPSHA? Well, if you're looking at, again, that Bernoulli equation, we have like 3 sets of terms. We have P1 minus PVP over rho G. Can we play around with this? Or we can change the vapor pressure of the liquid that you're transporting, right? We cannot change it. However, if you want to maximize that term, you can perhaps increase P1. So that would be the pressure on the surface of the tank. So if you increase the pressure at that station, then P1 minus PVP will also increase, and as a result, your NPSHA will increase. Now, there's Z1 here. Z1 is also positive on this side of the equation. So if you increase Z1, so it means that you increase the elevation of the tank, right? So you're going to raise the tank elevation. If you raise the tank elevation, then of course the NPSHA naturally is going to increase according to that equation. And last but not least, you've got here your kinetic energy term. But on this side of this equation, it's negative, right? So it means that when it increases, the NPSHA decreases. So what you want to do is decrease V2. And how to decrease V2, which is the velocity at which basically your fluid reaches your pump. Well, in this case, you can do that by increasing the suction pump diameter. And that's again because of your mass balance in steady state. If your initial V2 is initial, let's call it V2I, is basically too high, then remember that your mass flow rate m dot is rho to V2 A2, right? And your initial mass flow rate, we'll call that N2I. It's going to be equal to your final mass flow rate M2F, which will be rho 2 V2F A2F. So you got basically V2IAI equals to V2F A2F. So you want V2F to be less than V2I, right? You want V2F equals to V2I A2I over A2F. So this is your initial value for the velocity, V2I. And if you want to decrease it, then A2F must be greater than A2I. So you will have V2F less than V2I if A2F is greater than A2I. And so if you increase the pipe diameter, and that's pretty much it. So if we play around with either the external pressure of the feed, P1, the elevation of the tank, or the pipe diameter, then we can increase the NPSHA in such a way that our pump can operate safely. That's it. Thank you.